Does anybody have any questions on?
Yeah. Number 42 and 13.2. Want me to read it to you?
I like that. I want to curl it. Can you read it to me?
No.
42?
Yes.
Okay. Yeah, this problem still freaks people out sometimes. This is one that's got f of x and it says find all x. That one?
Mm-hmm. But in the bottom it says x equals 1, I think.
So we'll give you this here. And they say find all x where f of x equals 1. And for some reason people answer a different question. I always like that. They're like, I don't like that question. I have a better question. I'm going to answer that one. I'm like, no. So if you plug a 1 in, you're answering a different question. That question would be find f of 1. Then you would plug a 1 in, right? But this one says find where f of x equals 1. What is f of x? But what is f of x?
1.
Yeah, I want f of x to be 1, but what is f of x?
Something like that.
Yes.
Oh, okay.
So replace that with what it is. And you want that to equal 1. And again, this is just kind of a reminder that the math book every now and then says, hey, all that math you learned before, it could show up any damn time it wants to. All right? So don't go, we're not in chapter 7 anymore, I don't care. I think 7 was the one where we did this kind of things. How do you solve this? Does somebody remember? I love it. So don't forget that guy has just a 1 on the bottom, poor little dude. So what is he missing that other people have? X plus 4, exactly. And what's he missing? An X. And what's he missing? Everything. Damn. Such a neat little thing. Remember that? Sound familiar? Yeah. So the point of math is not to know something for a little while. The point of math is to understand something and keep it going. So the reason this shows up now is because when I do this, I'm going to end up with a quadratic. And every time we did this back in chapter 7, they were factorable. I don't know if you realize that. And I had to make sure that they came out factorable when I made a problem. Now it could be any damn thing because now we know quadratic formula, right? So if I can't factor it, no big deal. I just plug it in quadratic. I get complex numbers. I'm not freaked out. Put the i's on there. I'm done. So what do we get here? What could I do next? What was the whole point of that? Yeah, so I got all the LCDs. So what could I do now that's really nice because it's an equation? What can I always do with an equation when I have fractions in an equation? Yeah, I can kill them, right? Funny, one of my students said, he said something about killing, and their new teacher said, oh, you had Mr. Waller. So if you say killing to somebody, then, oh yeah, it's Mr. Waller, it's violent shit. Let me see, do I have a third? Do I have a tertiary color? No. Alright, too bad for all of us. So if I multiply everything by x plus 4, it'll cancel everywhere. So what's left here? 7x plus 28 plus 7x equals plus 4x. Oh, scheisse. And of course, this is old news. What tells me what to do? What part of this equation tells me what to do? The exponent, the square. Since one of my x's is squared and the other ones aren't, I have to get everything on one side because I want to equal it to 0. And then I try to factor it, and I'll bet you anything it's not going to factor. So in here I got 14x plus 28. Subtract 14x. Subtract 28. Does that factor? Hell no. Only things for 28 would be 4 and 7, 14 and 2, nothing that's going to make 10. But we don't freak out, we just do what?
Oh, quadratic.
Quadratic, yeah, we just do quadratic. I like it. If it doesn't factor, you just apply quadratic. If it's equal to 0, you try to factor it, because that's the way we used to do it. That's the quickest way to do it, if it factors. If it doesn't factor, you can use quadratic. You can even use completed square if you really like completed square. But like we saw the other day, quadratic is a shortcut to completed square. Right? It was built off of completed square. Is that, who asked that question? Is that enough to keep going? Okay.
I just didn't know how to start it.
All right. Cool. So at least you got you there. All right. Anything else from, yeah?
13.1 number 25.
Oh, cool. All right. So I want to compare this to what we're going to do there. See, how many x terms are there? Do you see what I mean? How many terms with x in it? 2. So that kind of tells me, if my variable, so this is number, sorry, which one, 25? Mm-hmm. Yeah, so this is back in 13.1, right? 20, you can make a, sorry, I don't know my number 2 very well. Hopefully it doesn't bother you guys. You can do this 2 different ways. The weird way is to factor this, because we're not used to being able to factor sum of squares. Is that? How many variable terms do I have? 1. So I can actually isolate that variable term and then isolate the variable itself, right? How do I do that? Subtract 81 to get this stuff by itself. Now start to isolate your variable. Become a negative 81. There you go. How do I isolate my variable? What's the first thing I should do? Divide by 4? I like that. And as you say that, I'm like, oh yeah, she just said that. She's very patient, though. This is good. And then square root. Kick ass. And the minute you square root something, plus or minus. And we are beyond the point where you balk at having a negative there. What's going to show up? I. So what's the square root of 81? What's the square root of 4? Plus or minus, and we put in I. Done. Because the square root of negative 1, I can take that separate. That's I. And the square root of 81 and 4, I can do that separate. That's 9 over 2. That's easy. And the plus or minus are still there. So it's only when our x terms are kind of separated. We either have to use completing the square to kind of force them together, so then we can take a square root, or we use quadratic formula, which is a shortcut. When my only variable term, I only have 1, that kind of kicks ass. I don't have to do quadratic. I don't have to do all that. I can just get that and then square root. I can do it directly. So it's important to know, what do I look for in an equation that's going to tell me what to do, right? And it's nice that equations tell you, hey, here's how you solve me. You're like, man, can every equation do that? Please. Okay. Yeah.
I have a question about like just the theory of it. Like, so how would you graph that? Like, what would that look like when you put an I in the
I love it.
coordinate?
So that's sort of related to what we got into last time. Very quickly, just to make this a quicker discussion, is it okay if I just take the 4 off? Let's just look at this. Is that all right? All right, just to make this easier. And this is still not that easy, to be honest. But d squared, let me change it to x, just so it's more of what we're used to with graphing variable. If I wanted to graph x squared, we should all know what that looks like. Can you draw it in the air? Trenton did. There it is. Cool. So u, right? A nice curvy u. Absolute value would be a v. It's like, it just has this kink. I don't want to be in that plane that goes, oh yeah, boom, we're all dead. We can't change direction that quickly as humans. I'd much rather be in that plane. Yay. So if I go to graph this, if I graph this part, it would be a parabola at 0. What does this do to it? Moves it up. So this is going to be a parabola sitting at 81, right? And just to make it more in context, and that just made it easier for me to graph it quick. And if I solve this equation, I'm trying to find the x-intercepts. Now, looking visually, are there any real x-intercepts? No. And this is this is the real plane. Every number that's on here is real. Is there anywhere for complex numbers to show up? So it's interesting. I want you to realize just a little taste of this. This is not the full story. This is only a real plane. This function looks very different in the complex plane. Because is there anywhere for a complex number to go here? These are all real numbers, aren't they? That's 1, that's 2, that's 3, that's 81. Those are all real. Any eyes on that thing? No. These are all real. So that's why it only makes sense that if I solve that equation, I get complex numbers. They're not going to show up on this graph. Because this is a graph of real numbers. Thank God, right? Complex graphs get really neat. You graph with colors then. It's cool. And the darker the color, the more imaginary the number. So if you look up something called fractals, a lot of fractals are based on plots of complex equations. And some of you guys are like, dear God, dude, is this something I got to know? Please stop. Please stop. But if you're at all interested, you just have to look at it. Fractal pictures are kind of cool to look at. But when you see all the different colors, very often they relate to how imaginary something is. They're darker if they're more imaginary. They're lighter if they're not as imaginary. It's neat. We're not going to do that. You don't suddenly have to buy a bunch of color pencils and pray that you color in the right thing. If I solve this, how do I solve this? Subtract 81. Square root. Plus or minus? Plus or minus? 9i. So those I cannot find on here, and again, because they're imaginary, they're not going to show up on a real plane.
How come you're allowed to split up the 81 and the negative 1? How come we can do that?
Let me ask you this. How do you simplify this?
25.
What'd you just do?
Oh.
That was the appropriate response. I like that. So when I have, 25 and 2 are numbers, I can split them up because I'm just undoing the multiplication. They both have the same root, right? So I'm just doing the opposite of multiplying. I'm just splitting them up, factoring. So if I have square root of negative 81, that's the square root of negative 1, square root of 81. Square root of 81 is 9. Let's put them in the opposite order. Square root of negative 1 is 1. Same way as 50 is broken up as 25 and 2. There's nothing different. Negative 1 is a number, right? Shouldn't have to march through the streets. Oh, I am a number. We know he's a number, so we can split him up. Just like we can split 25 and 2.
Okay. Thank you.
I am a cold medicine. You never know what's going to happen. All right. Okay. Is that cool, Trent? That's a really, really good question because it really gets into some freaky stuff. So it's really interesting to realize we can do the math with complex stuff, but the graphing of it is well beyond this. In fact, it's beyond my Math 280 students. So I'm just saying it's up there. If you search for fractals, you can actually see graphs of complex numbers. You can see it. It's cool. All right. Anything else from homework? Yeah.
13.1, number 75.
Oh, good. All right. So I'll do the first couple steps here. So it says solve by completing the square. And to remind you to divide first to make the first number 1. This is the one, right? Mm-hmm. Okay. Because completing the square only works when this is 1. So what's the very first thing I should do? Or maybe it could be the second thing. Because what's the first thing we normally do when we're going to complete the square? We got to make some room, right? We got stuff we want to add. So who's in the way? Minus 3. So we get him out of the way. Get over there. Now I got some room to play with, right? And now we can also do what? Because I can't complete the square because the first number is a 5, so I just divided by 5. Now, it makes my problem kind of gross. Right? But that's just too damn bad. I desperately want you to realize that at least don't feel like this looks disgusting. But completing the square does the work for you almost, if you allow it. What are the steps for completing the square? You take 1/2 of what? Yeah, the thing in the middle. So I'm not gonna write it as 4 over 5 over 2. That just looks disgusting. I'm gonna say half of. So if my middle term is a fraction, I'm gonna write divide by 2 as a fraction, 1/2. So what happens? So I get 2/5, and then what's the second step? 2/5 squared is 4 over 25. So what am I going to do with 4 over 25? Good. That's what gets added here and here. And then what does this tell me? Good. It tells me how this thing is going to factor. It factors it for me, which again is really, really, really nice of it. So that's plenty. I think I did plenty. You see, I mean, ugly looking numbers, but the process kind of eats them up for you. Now you have to get these together. But if you're complaining about LCD on fractions, I'm going to have to ask you to leave. Okay, cool. And just to remind you guys, now my only variable term, how many variable terms are there? This is going to be a little weird, maybe. There is only one term that has an x in it. This one. So I can square root it, and whatever I get on the other side, square root it. See, that's what completing square does. It consolidates all my x stuff so I can square root where they are and kill that square. Cool. Yes?
I have a question for 13.8, number 15.
All right, so we're going to answer that as soon as we lecture on it. Yeah, that was a freak one. I haven't even lectured on 13.8 yet, so we'll get into that right now, I think. I'll remind you what we did last time, and then we'll do some. I know it's been too long. So you get your regular dose of word problems in section 13.8. You're all just itching. Word problems, please. Here they are. But to remind you what we did last time, if I have this, how do I find the vertex? What's the quick way to find the vertex now? Beautiful. So the x piece will have to be negative b over 2a. And that is directly from the quadratic formula, because it's negative b over 2a plus or minus stuff. So if I know the intercepts, the vertex is going to be right in the middle. Well, negative b over 2a is right in the middle of that equation. That's the one that gives you the intercepts. So it really just makes sense. It's awesome. And then that's beautiful. That's lovely. And then that's the x piece. But what's the vertex? It's a point, x, y. How do I get the y piece? Plug it in. Cool. Two-step process, because there's two parts to the point. So let's do a specific example. I don't know. Let's do that one. So we'll steal that quadratic piece from that last problem. So how do you find the vertex? This can be nice and gross. Yeah, so it'll be negative b, and b is 4. Negative 4 over twice a, and a is 5. Negative 4 divided by 2. Yeah, so negative 2/5. So that's what negative 4/10 reduces to. Cool. And that is the what? I should always put that. That's the x piece, right? That's the x piece of the vertex. How do I find the y piece of the vertex? You do something you really don't want to. Plug it in. So I need to know what is f of negative 2/5. That's 5 times negative 2/5 squared plus 4 times negative 2/5 minus 3. Let me put this up here. Oh, and yeah, let me see. If I, bear with me for a second. If I do this, this will be 15 plus 4 is 19 25ths, right? Is that cool? Keep that in mind. And then you finish that out. That's to solve it. All right, let me put this up here. Oh, shit. This looks weird. So how do I do this? What's negative 2/5 squared? Yeah, that sounds familiar over there, right? 4 over 25. So you get 5 times 4 over 25. Plus 4 times negative 2, so that's actually minus 8/5 minus 3. Now, anytime I do a problem, the most important thing you can focus on is what the process is. If you get lost in the specific problem's work because the numbers are weird, focus on the process. What did I do? Negative b over 2a got me started. I got the x. I plug it back in to the equation. There's the equation, Jeff. Plug that back in to get the y. So that's what I'm working on. It just happens to be an ugly number I'm working with, right? But the process is relatively simple. What happens here? Yeah, 5 goes into 25. So I get 4/5 minus 8/5 minus 3. Yeah, negative 4/5 minus 3.
Well, you're gonna get that. You're gonna get that.
Sorry.
19 on.
I'm sorry. I didn't mean to.
No.
But we will. If you said something one more time, you'll yeah, because now LCD, so it'll be 15, negative 4 minus 15 is negative 19 over 5. Almost that. It's got me concerned, but I'm not going to think too much about it. So the process is do this first to get the x piece, and then you plug it in to get the y piece. So my vertex here would be negative 2/5, that's the x piece. Negative 2/5 is the x piece. And the y piece, negative 19/5. Okay, cool. How we doing? Not too bad, right? All right, so here's how that plays into, and to be honest, most of the problems are not real word problems on assigned because they already give you the equation. What makes a word problem is you got to make your own equation. If they give you the equation, it ain't a word problem. It's a plug and chug problem. So let's do one plug and chug problem, and then we'll do one not so pluggy problem that you have to make up your own equation. Let's see. So let's see, like number 8 says the number of pounds of milk per day recommended for a calf that is X weeks old. So we have an X week old calf. And the number of pounds of milk it should get is represented by P of X. Alright, so if I had a 5-week-old calf, I would plug the number 5 into the function to see how much milk it should get. Alright, that's a nice, I want equations to help me. If I ever had a baby, I'd want a bunch of equations. This is how long it should sleep. This is how much stuff it should get. Please let me do that. Where'd it go? There it is. So here's the equation. The pounds of milk is negative 0.2 square x squared plus 1.3x plus 6.2. So if you had a 1-week-old calf, you would plug the number 1 in, you'd see how many pounds of milk it needs. So the question is, When is the calf's milk consumption the greatest? So can somebody tell me about something about this function? What would it look like visually if I graphed it? Tell me some things about it. If you graphed it, what would it look like? Cool. Yeah, it definitely has a shape of what letter? U. And is it up or down?
Down.
Yeah, why is it down?
It's negative.
Because it's negative. It's a lot sort of related to slope, right? But not slope because this is not linear, right? So that first number is a negative. If the coefficient of the x squared is negative, it's going to be a down parabola. If it's positive, it's going to be up parabola, right? And it makes sense. And the question makes sense. If it's a down parabola, does it have a maximum? Yes, it's got a top of the hill, right? So how do I find that? So I know it looks like, get out of there. Let me just have it. I know it looks like that. I know there's going to be a maximum. How do I find it? What is that also called?
Vertex?
Vertex. How do I find the vertex?
Equation?
I like that. Some of you guys looked over. Yeah, come on, look at this one. That was awesome. Yes, you do that. So find the vertex, two-step process. You first do negative b over 2a. What's b? 1.3. What's a? Yeah, let me take that. Negative 0.2. All right, looks like 3.25. So what's that represent? What's 3.25? 3.25 what? Light years, 3.25. What? Banana peels,
The consumption?
3.25.
Pounds?
2.25 milk. Oh, never mind. Weeks.
Yeah, just look back to see how the variable was defined. You can do the same thing in the problem. You just look back to see. Why does it make sense that this is a pounds equation? Because it's a P, right? So if it would have been an equation for weight, it would have been a W. It's kind of good. That's another reason why function notation is nice. We can actually make the letter we use related to the physical thing we're talking about. P for pounds. Kick ass. Not L. Freaking LBS. Whatever. All right. Have I answered the question? When is milk consumption greatest? After 3.25 weeks. Okay, I answered the question. There's a second part of the question. How much milk does it consume at that time? How do I figure that out?
You plug it in, right?
Plug it in. It's silly. So the two parts of a vertex are where something happens or when, and what happens there. Right? So normally, like this axis is time. So after 4 weeks, this happens. So at 4 weeks, at this position, this is what happens. Where or when, and what is the output. Right? So they could ask two questions. When does it happen? That's the x piece. What happens? That's the y piece. So you plug 3.25 back in. Negative 0.2. You can use your calculator. Plus 1.3 times 3.25 plus 6.2. Plug a 3.25 back in. Can somebody with the calculator help me? Who is it?
12.32.
Sure, man. 12.53. 12.53 what?
Pounds of milk.
Yes. All right, sweet. I was hoping I wouldn't have to go through anything. So at 3 1/4 weeks, a calf should consume 12.5 pounds of milk. Will every calf do that? No. So this equation is actually interesting. It's sort of an average of observed behaviors of calves. So it's sort of like if you ever had a kid, you see these charts that tell you the normal height, and they have like the 99th percentile and the first percentile. So you can see if your kid has got the normal height, and they're not like or in the weights too. You can see if your kid is like me. I was a real chubby little dude. I was always at the top of the 99th percentile, little Buddha. Right, because my mom just kept feeding me everything. Here, shut up. Have this. So I was at the top of that. Anyway. And it's just an average. It's just The line in the middle is established. It doesn't matter if you're above it or below it. It only matters if you're really above it or really below it. So if your calf is taking in 10 pounds of milk and it's only half a week old, that could be a problem. That's probably not something good. Something bad's happening. Right. It's got something else inside of it that's eating its food or something. Let's not get too deep into that. Okay. All right. So let's do one now where we have to create our own. So like number 11, sure. Number 11, we got furniture designer. He wants to make a rectangular table. We're going to look at it from above. And he wants it to have a perimeter of 128 inches. So I want you to consider this, and I want to know what's the max area. I'm just going to feel for why that question makes sense. The perimeter is 128 inches, so can somebody help me out? Let's just try a few, what can I call this? Possibilities. Let's just try a few possibilities. To make a perimeter of 128 inches, can somebody give me, just give me what the width might be? Just give me a width.
37.
Who?
12?
37.
Okay, we'll go with 37. So this would be 37. Now, how much is left for the length? There's 120 inches total. How many inches have I used already on the width? 74. So how much is left over? 54. Which means how much would each of these be? 27. All right, so we're going to ignore the fact that Arby's length is shorter than his width, but that's all right. Peace out. What's the area of that? Good, 27. And what's 27 times 37? Somebody help me out. Somebody help me out?
I don't have.
999?
Really? That's fine. That's possible. It makes it 7 times 7 is 49, so it ends in 9. That makes sense. 999 square inches. Is that cool? Now, just bear with me now. This is nothing you have to do. This is me doing my weird shit, but I'm just investigating what could the table look like. So in actuality, this table would look like, let me just put this right, 27, 27, 37, 37. Now, I heard somebody else said 12 inches. Maybe the width is 12? So how much is left over for the lengths? Yeah, 104. So each length would be 52. So it could look like that, or it could look like that. Right? Let me actually make this a little more extreme so we can really see the difference. So it would be longer but less wide. So it could look like that. Do you see what I'm saying? So it could be this long and just a little bit less wide. Or it could be really long and not so wide. Right? What's the area here? It's 24. Sorry. Yeah. What happened? What happened? Did the area get bigger or smaller?
Smaller.
Smaller. So it seems like the closer I am to being a square, the larger my area is. So probably a square would maximize the area. We're going to prove that to be true, and it's always true. If I have a four-sided figure and I want to make the maximum area, a square will always be a bigger area than any rectangle. Right? Now let me go one step further real quick before I finish this problem out. What shape are silos in? You know, where they put grain and corn and stuff. What shape is that in? Cylinder. So it's circular, right? At the base, and then they just build it up. So a circle will always have more area than a square with the same perimeter. And they actually figured that out before they had math really to back it up. They just kind of knew it by trial and error. They knew that a circular thing would hold more grain than a rectangular thing. So they want to spend less money. They don't want to use more material to make it, so they make it circular. Whoop, and then it holds more stuff. Saves them some money, right? Obviously, if you want to stack boxes, you don't want a circular thing, do you? Because then you're wasting a lot of space. So, but if you have little corn grains and stuff that'll do it, then that'll fill it all up. That's beautiful, right? Ooh, it's a real life math thing. Math came in later and said, "Oh yeah, you're right." That's a nice thing where people's brains beat math to the punch. So let's actually do this problem now. We just played around with what could be true. Let's find out what really is true. This is weird though. What's the equation? And actually, let's give some variables here. What do I not know? What do I not know that I kind of gave us values for here? Yeah, I don't know what the width and I don't know what the length is. So I basically don't know much of anything. But I do know something here. How does that relate to these?
You divide by 4.
Well, that's if we know it's a square. We got to prove that it's square. Do you see what I'm saying? I can't start there. I have to prove that it's square. I'm not going to get a 4 anywhere. What's the perimeter of this? Don't tell me 128. What's the perimeter of this shape? 2 L's and 2 W's. And what is that supposed to be? 128. If it was a square, then I could just say 4x equals 128, divide by 4, and be done with it. But we don't know. It seems like the more square it is, the better, but we don't know. We're going to prove it. What can I immediately do? Yeah, divide by 2. So I get this equation that I can use. So this is a 2-step process for this. So when you have to create your own equation, it's almost always going to be a 2-step process. They're going to tell you something. They told me the perimeter, right? And they're going to ask me something. They ask me about the area. What is the area of this? L times W. Kick ass. So the thing they ask me is the area. And the area is L times W. Now what sucks about this equation? How many variables are in here? 2, that sucks. I want 1 variable. I can do something with that. So what can I do? There's too many variables. Damn it. If only I knew something else about L and W. What do I know about L and W? Yeah, so what can I do with this equation?
I'll split it.
I can solve for, doesn't matter. I can solve for L. How do you solve that for L? Subtract W. So I know L is 64 minus W. So then what can I do with that?
Plug that in.
Plug it in. So now I know the area is L, but what's L?
64 minus W.
Become a minus W there. Times W, right? Is that cool? And what can I do with what I just wrote down? Distribute. And can somebody tell me something's wrong with the ordering of that compared to quadratic stuff that we work with? What's wrong with the order? Where's the highest power?
Oh, in the second.
At the end.
Yeah.
So you've got to really be careful about is you got to identify what A, B, and C are, and people make a mistake with this. They say that's A, and B is -1, and that's completely wrong. A is in front of the squared term, so if you just put it in the right order, you won't make that mistake. So now look at what we got. The area is modeled by what kind of graph? What would that look like if I graphed it? Good. I like it. Very animated, isn't it? That's what it would. So yeah, it would look like an upside down parabola, right? Because it's squared is the highest power. It's got a negative in front, so it would be an upside down parabola. So why does the question make sense? Because an upside down parabola has a max, right? So they ask for a max, and you get something like this, you know you made a mistake. You're like, holy shit, that doesn't really make any sense. So if you're paying attention, if they don't give you an equation to work with, this is the steps to take. I like my grammar. This is the steps. So how do I find the vertex? And normally I say x equals negative b over 2a. What's acting like x? Careful. A is acting like the output. W is acting like x, right? So the width is negative b over 2a. And what's b? 64. And what's a? Negative 1. So the width is 32. What's the length? 64 minus that. So the length is 32 what? 32 inches. And that means if they're both 32, that means that this is a square. Cool. So a square is the maximizer for that kind of thing. It's kind of nifty. So if you're allowed to have all four sides, a square will always maximize your area. There will be problems where they have like a river and they want to put a pen for an animal that can't swim, so they don't need a fence on that side, right? So then you don't have all four sides. Then it won't be a square. It won't be a square shape that will maximize. You want to give it the most area to play in, right? So you're going to maximize the area. You don't want to do this to it. You don't want to say, have fun. Can't swim, I know, but I'm going to put you right on there. No, you want to maximize the area for it to play in, right? Unless you're really evil, in which case you'll do that. But then it won't be a square. That's my point with it. Yeah.
Doesn't that make 32 inches make the length and the width the same? If it adds up to 128%? 32, 64.
Yep, totally. It's got to. It's the answer to this question, so it's got to be 128. But you can check it, yeah. If you 32, 32, 32, 32 makes 128, thank God.
Okay. I thought the length was always supposed to be a lot bigger.
Oh, we went into it, we didn't know. So we had to assume it was a rectangle.
Okay.
Now we know, oh, it's a square. We didn't know.
Okay.
I like it. Okay, cool. And just a little bit on number 15, since somebody asked me about number 15. I like 15. I would like 15. So 15, you start with a sheet of metal that is 8 by 14 inches. And then they bend the ends of it up to make a gutter. I'm going to put this up on a roof. So you want that gutter to hold the most stuff it can, right? That's the point of a gutter. So you don't want it to be flat, and you don't want it to be like this, so then it can't hold shit, right? So you want it to be somewhere in the middle that maximizes the area. So if I bend these up, bend those sides up, do you see that? Do you see the idea? So that's going to be where I bend it, because I'm strong. No, purpose. And this is going to be my unknown. I don't know how much I want to. I probably don't want to bend it there. No, that's probably bad. And I don't want to bend it right in the middle and then just make it flat. That doesn't make any damn sense, right? So they give you the picture in the. But tell me this before we draw this. Let me see if you guys can get this. How long is this? I like what you're thinking, but no.
2x.
This is 2x. The whole thing is 14, so how much is left in the middle? 14 minus 2x, right? 14 minus 2x must be what's in the middle. 14 minus 2x. Holy shit. So then they give you the picture. Now if I bend these up, all right, let me see if you guys can come with me. If I bend these up and then face it to you, bend it and then face it to you, it looks like this, right? Is that cool? And how tall are these? X. And how long is this? 14 minus 2x. So what's the area? of that. How much can it hold? How much can it hold? What's the area of this? X times that, yeah. And look, it's a parabola that opens down up to, it's just like the one we just did. All right, I did more than the 1 and 2 there, sorry. Y'all, it's okay, Jeff. You can do that anytime you want to. I'll let you guys finish that one now. It's number 15 in the homework. 113.8. All right. So you got to get in there and try those. Most of them, they give you the equation. It's just, you got to pick out B and A and plug it into negative B over 2A. Go forward. It's really freaking awesome if you let it. It's actually really simple of an idea. The negative B over 2A, bam. It's called optimization problems. You want to optimize your profit. You want to optimize the area that something can hold, right? Optimize your cost means minimize it, right? Okay. So I want to talk a little bit about section 14.1 and in general what we're getting into. I can't let you escape this class without talking to you about logarithms. Right. Has anybody ever heard anything about logarithms? Sounds like it might be some kind of a nice thing you can dance to, but it's not. It's too bad. Anybody know what a logarithm is? No? Alright. Well, you will. We'll get there. People hate it, but I try desperately to show you. The only thing that really is bad about logs is it's a symbol I'm not used to. That's it. And we're not used to having a symbol be log. That's the symbol for the function. Right? I can deal with a square root symbol that tells me cut the thing in half. I understand that. So the most important thing you have to get down is what does log mean when I see it? What is it asking me to do? Once you get that, it's simple. But you can't just look at log and go, oh yeah, that means, no, what the hell? You got to internalize what that means. The first thing I want to do, we have to kind of create them. So section 14.1 is laying the groundwork for what we need to be able to create logarithms here later. So we start with what's called composite functions, and then we get into inverse functions. So composite functions, let me see if you guys are able to handle this idea. We've sort of already done these. Alright, so you have these two functions. Now let me just do a little reviewing too. Let me give you some warm-up questions. They should be relatively simple. Can you figure out, take a minute and figure out what f of, what you got, Jeff? I don't know, man. I'm trying to make one come out nice for you. Screw it, it's just not going to. Figure out what g of -3 is. Figure out what, yeah, sure, you could do this, what f of 0 is. And figure out what g of a is. Do those three first. Alright, so what's f of 0? I love it, kick ass. You plug a 0 into the function of f, 3 times 0 minus 1, the square root of negative 1 is I. What about g of negative 3? And when you plug negative 3 in, you square it. You plug a negative 3 into g. 9 plus 2. So you can ask, right? Function notation is not very weird. It's not. It's just substitution. And what's g of a? Careful. G of a is a squared plus 2. Done. I didn't say it was equal to 0. I just said what's g of a. If g of x is x squared plus 2, g of a is a squared plus 2. It's almost too easy to realize. You look at it like, what the hell am I supposed to do with that? Put an a in. Can you do a squared? What's a squared?
A squared.
See, so you can't. Right? So you can't do anything. You're done. You're done. There's nothing to do. Here, could you do negative 3 squared?
Yeah.
Yes, so I had to keep going. So it's almost better if it's just a letter. You're like, oh good, I'm not going to have any work to do once I put it in. I'm done. All right. So let's go one level up.
Log is exactly like this, right?
Huh?
Log is very similar to this.
Log?
Yeah.
No. Sorry. All right, here we go. You ready?
Yeah.
What is f of 5 minus 4x? See if anybody can hang with that. Just think about what we did for g of a. And then do the same thing. All right, so let's see. Do it here. So whatever's here, I put it there. That's the idea. Nothing more, nothing less than that. So f of something is radical 3 times that thing minus 1. So I just replaced x with that. That's the single-minded thing that functions do. And then you simplify if you can. What do you get?
15 minus...
Yeah, 15 minus 1 is 14 minus 12x. Done. And of course, the mistake people make, I'm not picking on you, RB, but everybody does it. They make it equal to 0 somehow. And there's such a bleak outlook. Everything in the world is 0. Very nihilistic, right? These guys from Big Lebowski. Very nihilistic. Everything is 0. I'm going to go write some poetry about that. All right. So here's the next step. The next step would just be this. What's f of g of x? Why is this different from D? What did I put inside F in part D? What is inside F in part D? No, part D. What's inside F?
5 minus 4x.
5 minus 4x.
Yeah.
So I told you explicitly what the thing was I wanted you to plug in. This I'm saying plug g of x into F. What the hell's g of x? Yeah, you do. What's g of x?
Oh.
So it's f of x squared plus 2. So then if you were able to do part D, you should be able to do this. So they just weren't being totally explicit with me. And I got to go, oh shit, I got to go look at it. Thanks, problem. All right, it's this. Stupid problem. You could have just been like part D. Dork. So then how do I do that?
Plug that in.
Square root 3 times that minus 1. So I get square root of 3x squared.
Minus 5.
Good, well, careful. Plus 6 minus 1 is
Oh, plus 5.
plus 5. Cool. I like it. So just giving it its functional name is not any different from what Part D was. And I'm not saying Part D is necessarily immediately obvious and easy, but it wasn't that difficult once you get the idea. Just whatever the hell's in there, you put it in. So here they said, plug this secret thing in. Well, shit, we got to go look at the hell it is. And then I can plug it in. Not a big deal. This is what's called composite functions, because that function is composed of another function. Right? It's a function composed of multiple functions. So, ooh. All right, let me see. Let me give you a freaky one, because that was not a freaky one. That was a nice, easy one. Here's a freaky one. Still with the same functions here. What is g of x? No, that's g of x. What is g of x? Like that is a person with a stutter, I think, Jack? No. Don't need to make light of stutter. So what's your first step? First step is towards the door, Jack. No. This is g of what? X squared plus 2, because that's what g is.
That's what I told you.
Cool. I'm with you. I'm catching up to you. And then what do you do with this? Well, you told me the answer was this.
No.
The answer is put this in to itself. Now that's some freaky shit. All right, that's some function inception stuff. So x squared plus 2, I got to put it in. So that whole thing goes there. So it'll be x squared plus 2 squared plus 2. And then I can FOIL this, x to the 4th plus 2 to 4, x squared plus 4 plus 2 is 6. Blah, blah, blah. You guys can do that. FOIL it and then put your like terms together. Not a big deal at the end there. Just simplify it if you can. Coolness. All right. All right. So that's the idea of composition of functions. All right. Well, if you understand functions, those are really relatively simple. I want to talk a little bit about inverse functions, and then we'll head out before my cold meds run out. So inverse functions are exactly what hopefully they sound like. They're somehow opposite functions. So if I said f of x equals x plus 5, what do you hope its opposite function would be? What do you think? What's your gut instinct tell you? What's the basic idea of f of x? What's it doing? What's f do to something? What's f do to something? Whatever you put into it, what does it do to it? Well, you can do it. If I put a 2 into it, what would you do to 2?
Oh, like that.
Well, yeah, what would you do to it? What would you do to it?
Add it to 5.
Yeah. So if you put a 2 in, you would put 2 plus 5. If you put a 7 in, what would you do to it?
7 plus 5.
Add 5 to it. If I put a 5 in, add 5 to it. Right? Whatever the hell I do, I add 5 to it. What do you think the opposite function does?
Subtract.
Oh my God. Subtract what?
5.
No way. Shit. So what would it look like?
So,
They're opposites of each other. Hey. So that's what you would hope inverse means. And it's exactly what it means. It's just that was easy because addition and subtraction is easy. The minute I start combining shit, it gets a little bit harder to tell. All right? That's the basic idea of inverse. And let me replace this immediately with its actual symbol. The inverse of f is officially given this symbol, which actually kind of sucks because students look at that and they think that means 1 over f, which is completely wrong. This is a symbol that means the opposite of f. I wasn't around when they came up with it, so I couldn't point out, hey, that's stupid. Let's not do that. It's too late. Everybody now thinks that. I'm like, shit. So if f of x is x squared, f inverse is not 1 over x squared. No, all that crap, just mark it out. That does not mean flip it. That's not what it means. It means the opposite. So what do you think? If it's x squared, the opposite should be somehow related to the
Inverse.
which is, what's the opposite of squaring? Square rooting. There you go. So the inverse function should somehow have a square root in it, right? Okay, cool. So, if I have a function, let's do a specific function. Let's do 2x. Now bear with me for a second. You wouldn't have to do this. I just want to do this just to show you what's going on. So if I put a 1 in, what do I get out? 2. That's crazy. If I put a 3 in, I get
4. 6.
I tricked you. That's my fault. This is true. You were ready for that. Everything's like 2, 2, 2. No, shit. All right, that's enough. What do you think its inverse function is? What's that function do to anything you plug in? It doubles it, right? It multiplies by 2. So what do you think the inverse will do? Divide by 2. 2. Good. Now watch. If I put a 2 there, what do I get when I put a 2 in? 1. What do I get when I put a 6 in?
-3.
3.
Okay, no, I'm just going to not say anything.
That's all right. I still can. I'll just look at you. Do you notice something about these?
Flip.
1, 2, 2, 1.
Yeah, they
Kind of makes sense. If 1 goes to 2, if that function makes 1 become 2, and this undoes things, it's going to make 2 go back to 1. It's going to undo what happened to it. So one guy stretches it, it's twice as many. The other guy's, yeah, screw you, it's now and that's back to. They're opposites of each other. Is that cool? And here's a funny thing. So basically what happens to x and y between these two? They switch. It's crazy. Now watch. These are the last 2 things we're going to do. I'm going to talk about graphically very quickly, and I'm going to talk about algebraically. And we're all like, yes, the clock is still there. See it. You guys are always so worried the clock fell down or something. You would hear that. Don't worry. So visually, if I had a function, I'm not going to tell you what the function is, because I'm a dork. So say this function goes like this. So I got a function that looks like this. Very funky. What points does that function go through?
3. No.
What points does it go through? So -2,
3.
-2,